The second reason why we love polar coordinates are because polar curves actually can give us parameterizations of curves, and they can do it in a fairly easy way. Here's what I mean by that. Suppose you have a polar curve, so you can solve it for r, and you have r equals some function of theta. Then you can get a parameterization really quickly. Here's what you do. You know that x is equal to r cosine theta, right? And y is equal to r sine theta. These are relationships that we were using before if we had r and theta to find x and y. But since r is actually f of theta, you really have x in terms of this parameter theta, right? Because the r is a function of theta, and then you have times cosine theta. Oops. And y is r sine theta. So if you had a parameterization, or you have a curve here with maybe theta between a starting angle and an ending angle, now you have a parameterization. You have x as a function of the parameter theta, and y as a function of the parameter theta. Theta between a starting angle and an ending angle to give you just a particular piece of a curve. Let's look at an example. Suppose we want a circle. We want to parameterize a circle of radius 4. So parameterize a circle of radius 4. Okay, well, no problem. We know that to describe that curve as a polar curve, you could do that circle of radius 4 as r equals 4. And if you wanted to go all the way around, then this would be sufficient. Just have theta go from 0 to 2 pi. That would go around the circle once, right? So there's a description of going around the circle once in polar, and that quickly leads to a parameterization. Let's see, x is r cosine theta, but r is 4, so we get x equals 4 cosine theta. Y is r sine theta, but r, again, is this function of theta, it's 4. So we get this parameterization of the circle. Piece of cake. This will come up quite often in the class when we need to parameterize something. If we can describe it nicely in some coordinate system, like in polar, then we can usually get a nice set of equations, a nice parameterization of that shape. Now, we already know on parameterizations how we can do calculus on parameterizations. So remember, when we had x was a function of some parameter t, and y was a function of that same parameter, then we could find the slope of the parametric curve. Remember, our idea was to take dy parameter, dy dt, and divide by dx dt. In any given space of time, dy dt would be the slope, and this would be how much you move over in the y direction, that's how much you move up, and this would be, if you had a one time step anyway, this would be how much you move over. So this is the rise over the run. That gave us the slope of that curve. So we can apply the same thing to parametric curves because every parametric curve yields a parameterization, right? In particular, you have x is some function of theta times the cosine of theta, and y is that function of theta times the sine of theta. Here I'm assuming that r equals f of theta. So now the only difference here is that instead of the parameter being t, the parameter is the angle theta, but it's still a parameter. It's a variable on the side here that's controlling x and y. So let's see what this formula yields. If we're careful here, we can get kind of a nice little value. Let's see. Dx d theta, we're going to need that. That would be the derivative of this product, which would be, let's say it's f prime of theta cosine theta plus, so the derivative of the first times the second plus the first, that's f of theta, times the derivative of the second, which is minus sine theta. Dy d theta is equal to, the derivative of this is the product rule, right? Take the derivative of the first times the second, which is sine theta, plus the first, that's f of theta, times the derivative of the second. The derivative of sine is cosine. So now we can find dy dx. We're just using this formula. The only thing that's different is the name of the parameter. So we're just taking dy d theta over dx d theta, and we get this. Let's see, dy d theta was f prime of theta sine theta plus f of theta cosine theta, and dx d theta was f prime of theta cosine theta minus f of theta sine theta. Now f of theta was r, so we could also write it this way. It's dr d theta, right, since r is f of theta, dr d theta sine theta plus r cosine theta, all over dr d theta cosine theta minus r sine theta. This gives us the slope of a parametric curve. Let's look at an example of how we could use this formula. So, sorry, it gives us the slope of a polar curve, right? Every polar curve, though, leads to a parameterization, and so that's how we're getting the slope of the curve. Let's look at an example. We want to find the slope of this function. R equals 1/2 minus the sine of theta at the point theta equals pi. Now, at theta equals pi, the sine of pi is 0, so r equals 1/2. So you have the point theta equals pi, r equals 1/2. That would mean you face the direction of pi and take 1/2 step forward in the direction that you're facing. That's this location right here. So what we're trying to do here is to find the slope of this polar curve at that point. We expect it to be a number that's positive, right? And it looks like the slope is less than 1. Let's just see what we get when we apply our formula. Remember, we had dy dx was equal to dr d theta sine theta plus r cosine theta all over dr d theta cosine theta minus r sine theta. Now in our case, dr d theta would be the derivative of this. The derivative of negative sine is negative cosine theta. So at any point, dy dx is going to be equal to minus cosine theta sine theta, so minus cosine theta sine theta plus r. That's going to be, let's see, what are we getting here? Minus cosine theta sine theta, oh yeah, plus r, which is, r is 1/2 minus sine theta times cosine theta, so there's r cosine theta, all over, in the bottom here we have dr d theta, that's minus cosine theta, times cosine theta, so we have minus cosine squared theta, minus r sine theta, so minus 1/2 minus sine theta times sine theta. Now at our particular point, when theta equals pi, we can plug that in. Let's see what we get. The cosine of pi is -1 and the sine of pi is 0, so this term disappears. And let's see, the sine of pi is 0, so that's just 1/2 minus 0. So we have 1/2 times the cosine of pi, but the cosine of pi is -1, so we have 1/2 times -1. That's all we have upstairs here. Now we have minus cosine squared. Now the cosine of pi is -1, so if you square it you get 1, but then there's a negative out in front, so we're back to -1. And then the rest of this is all multiplied by sine theta, right? So this number would be 1/2, but then the sine of pi is 0, and so that gets wiped out. So we have a slope. The negatives cancel. The slope is 1/2, right? So the slope of this tangent line then we know is 1/2. We got it from this formula, which followed quickly from what we already knew about the calculus about finding slopes of parametric curves. The important point is that every parameterization leads to a parametric curve, so we can kind of treat it that way.